February 15, 1928, Wilmington, Delaware. The chemical analysis reports from leading European textile laboratories would never fully capture what they declared impossible that winter morning. American chemists, attempting to create synthetic fibers using methods that defied everything European materials science said was necessary for durable textiles. Through the steam and precision of the DuPont research facility, polymer chains longer than anything nature had produced were taking shape with molecular control that seemed impossible to European observers. No silkworms, no cotton plants, no wool from sheep. Yet they were engineering fibers with strength that natural materials could not match. In European laboratories, textile experts required centuries of tradition to perfect natural fiber processing. Each material was essentially limited by biology, different properties, different weaknesses, different durability outcomes. Most declared synthetic alternatives would always be stiff, brittle, unsuitable for human wear. The Americans were operating with manufacturing philosophy the Europeans had never imagined possible. Controlled polymerization, molecular weight precision, draw ratios that aligned polymer chains like suspension bridge cables, $250,000 in pure research funding, 30 chemists working 12-hour days, production standards so precise that modern manufacturers would abandon them as too expensive. 8,000 miles from European textile mills, the most decisive materials revolution in manufacturing history was revealing itself, not in natural fibers, not in traditional methods, but in the systematic molecular engineering that connected every American polymer chain, in ways European chemical wisdom never thought possible. The Cambridge professors had published their findings with absolute certainty. Professor William Henry Perkin Jr.'s latest paper in the Journal of the Chemical Society stated it plainly. Synthetic polymer chains exceeding 5,000 molecular units would collapse under their own structural weight. His German colleague Hermann Staudinger, despite pioneering early polymer research, maintained that controlling large molecules in industrial quantities remained fundamentally impossible. The mathematical models were clear. The thermodynamic equations were settled. Natural fibers, silk spun by silkworms, cotton grown in fields, wool sheared from sheep, represented the absolute limits of what textile materials could achieve. Charles Stein stood in his corner office on the third floor of DuPont's Wilmington headquarters, studying the latest European research reports that his assistants had translated from German scientific journals. Outside his window, the Delaware River carried cargo ships loaded with imported silk from Japan and cotton from Egypt. American textile mills remained dependent on materials that nature provided, subject to weather patterns, crop diseases, and the biological limitations that had constrained human clothing for thousands of years. Stein had spent 15 years watching European chemical companies dominate global markets through superior research. German dye manufacturers controlled color chemistry. Swiss pharmaceutical firms led drug development. British textile experts set the standards for fabric quality. American industry excelled at mass production and efficient distribution, but the fundamental innovations still came from European laboratories. But Stein believed American chemistry could challenge European tradition through sheer determination and unlimited research funding. He had convinced DuPont's board of directors to invest in pure science with no guaranteed commercial outcome, a radical departure from American industry's focus on immediate practical applications. The company would commit $250,000 to hire the brightest chemists available and give them complete freedom to pursue theoretical research that might yield revolutionary breakthroughs. European firms invested in incremental improvements to existing products. American laboratories would attempt to create entirely new categories of materials that had never existed before. Wallace Carruthers arrived at DuPont's experimental station on a cold February morning in 1928, carrying a single leather satchel containing his Harvard research notes and a profound skepticism about his own abilities. At 31 years old, he had already published groundbreaking papers on organic synthesis, but he remained convinced that his work was inadequate compared to the European masters he had studied. His colleagues at Harvard described him as brilliant but tormented, a chemist who could visualize molecular structures in 3 dimensions while simultaneously doubting every conclusion he reached. Carruthers spent his first week at DuPont reading every available publication on polymer chemistry, filling notebooks with calculations that proved most synthetic approaches would fail. The challenge that Stein presented to Carruthers was both simple and impossible. Create polymer chains longer than anything nature had ever produced, then find a way to manufacture them in commercial quantities at reasonable cost. European experts had already explained why this couldn't work. Large synthetic molecules were inherently unstable. Industrial production required consistent results, but polymer chemistry involved too many variables to control. Temperature fluctuations of even 5 degrees could destroy entire batches. Molecular weight variations of more than 10% created products with unpredictable properties. The raw materials needed for long-chain polymers were either unavailable or prohibitively expensive to produce. Carruthers assembled a team of 30 chemists, many recruited directly from graduate programs at America's top universities. They worked in a purpose-built laboratory, facility that contained equipment most academic institutions couldn't afford, precision temperature controls, molecular weight measurement apparatus, and spinning machinery designed to test experimental fibers under controlled conditions. The team's official mission was to investigate the theoretical limits of polymer science. Their unofficial goal was to prove that American determination could overcome European skepticism about synthetic materials. By 1930, Carruthers had achieved his first major breakthrough with neoprene, a synthetic rubber that performed better than natural rubber under extreme temperature conditions. The polymer chains in neoprene contained over 8,000 molecular units, far exceeding what European theories predicted was possible. DuPont immediately began commercial production, proving that large-scale polymer manufacturing could generate substantial profits. But Carruthers wasn't satisfied with rubber. He wanted to create synthetic fibers that could replace silk in women's stockings, the most demanding textile application in terms of strength, elasticity, and durability. The experimental fibers that Carruthers produced by 1934 demonstrated remarkable properties. His polyamide compounds could be drawn into continuous filaments that stretched like silk but never broke under normal handling. When knitted into experimental stockings, they maintained their shape after dozens of wash cycles and showed no signs of the sagging or bagging that plagued cotton hosiery. The laboratory results suggested that synthetic textiles might indeed surpass natural materials in both performance and durability. Then the manufacturing reality struck them with devastating clarity. Creating strong synthetic fibers required controlling molecular weight within 5% precision, a tolerance so tight that even minor variations in raw materials or processing conditions could ruin entire production runs. The polymer chains had to align in perfectly parallel formation during the spinning process, like 50,000 microscopic ropes twisted together with mathematical precision. Temperature control during polymerization needed to be maintained within 3 degrees Celsius. Pressure variations of more than 2% could alter molecular structure in ways that weakened the final product. Even more problematic was the cost structure for their most promising experimental fiber, polyamide 510. This compound produced beautiful, strong filaments in laboratory quantities, but it required amino non-anoic ester as a key raw material. Manufacturing this intermediate compound would require building entirely new chemical plants and developing production processes that had never been attempted on industrial scale. The preliminary cost estimates suggested that synthetic stockings made from polyamide 510 would retail for more than $20 per pair, making them luxury items that only wealthy customers could afford. Carruthers spent sleepless nights in his laboratory, running calculations that confirmed what European skeptics had predicted. The chemistry worked in test tubes, but scaling up to commercial production presented problems that conventional approaches couldn't solve. Every polymer synthesis textbook explained why large-scale production of long-chain synthetic molecules remained economically unfeasible. The equipment costs were enormous. The raw material requirements were complex. The quality control standards were impossibly demanding. American determination alone wouldn't overcome the fundamental mathematical and economic constraints that made synthetic fibers commercially impractical. As 1934 ended, Carruthers realized that his team had reached the limits of conventional polymer chemistry. They had proven that American laboratories could create synthetic materials superior to anything Europe had produced, but they still hadn't solved the manufacturing problems that would make those materials available to ordinary consumers. European experts weren't wrong about the technical challenges. They were wrong about American willingness to completely reinvent the production process from the ground up. Conventional chemical engineering had failed. Only a revolutionary approach to industrial manufacturing could transform laboratory curiosities into products that would change how Americans lived. Gerard Berchet arrived at the laboratory on February 10, 1935, carrying a notebook filled with molecular diagrams that would revolutionize synthetic chemistry. The 28-year-old chemist had spent weeks calculating precise ratios for a completely different polyamide compound, one that avoided the expensive amino non-anoic ester that had made polyamide 510 commercially impossible. His new approach combined hexamethylenidiamine with adipic acid in exact proportions, creating polymer chains that could theoretically reach molecular weights exceeding 20,000 units while using raw materials that American chemical plants could actually produce at reasonable cost. Carruthers studied Berchet's calculations with the intense focus he reserved for breakthrough moments. The proposed polyamide 6-6 structure offered elegant symmetry. 6 carbon atoms in the diamine component matched with 6 carbon atoms in the acid component, creating polymer chains with regular, predictable spacing between molecular bonds. This symmetry wasn't merely aesthetic. It meant that the polymerization reaction could proceed with mathematical precision, allowing chemists to control chain length and molecular weight with unprecedented accuracy. European polymer research had focused on irregular molecular structures that produced unpredictable results. American chemistry would succeed through systematic engineering of molecular architecture. The first experimental batch of polyamide 6-6 emerged from Berchet's apparatus on February 23rd as a clear, viscous liquid that solidified into a tough, flexible material unlike anything the team had produced before. When heated to 260 degrees Celsius, the polymer melted into a honey-like substance that could be extruded through tiny holes to form continuous filaments. These experimental fibers demonstrated tensile strength of 45 pounds per square inch, significantly stronger than silk's 35 pounds per square inch, and nearly triple cotton's 15 pounds per square inch. More importantly, the polymer chains aligned naturally during the spinning process, creating fibers with consistent diameter and uniform strength throughout their length. But creating strong synthetic fibers required more than just superior chemistry. The manufacturing breakthrough came through precision engineering that controlled every aspect of the production process with tolerances that had never been attempted in chemical manufacturing. Carruthers and his team developed molecular distillation apparatus that could separate polymer chains by exact molecular weight, allowing them to achieve molecular weight variance of less than 2% across entire production batches. This precision eliminated the weak spots that occurred when polymer chains of different lengths were mixed together in random proportions. The spinning process demanded even more exacting standards. The team discovered that draw ratios, the amount of stretching applied to fibers as they solidified, had to be maintained at exactly 4 1/2 to 1. Less stretching left polymer chains randomly oriented, creating weak fibers that broke under normal stress. More stretching aligned the chains too aggressively, causing them to snap during the spinning process. Temperature control during spinning required precision of plus or minus 3 degrees Celsius at 285 degrees. Pressure variations of more than 1% altered fiber diameter in ways that created stress concentration points where stockings would develop runs. Each successfully spun nylon fiber contained approximately 50,000 individual polymer chains aligned in parallel formation like cables in a suspension bridge. The molecular engineering required to achieve this alignment was unprecedented in chemical manufacturing. European textile production relied on natural fibers whose internal structure was determined by biological processes that humans couldn't control. American synthetic chemistry created artificial structures that were engineered to specifications more precise than those used in aircraft manufacturing. By October 1936, Carruthers' team could produce continuous nylon filaments for 10-minute intervals, long enough to knit experimental stockings but not long enough for commercial production. These prototype stockings revealed both the promise and the problems of synthetic textiles. The nylon wouldn't accept conventional flesh-colored dyes, turning an unnatural black color that made women's legs appear artificial. The polymer's smooth surface felt strange against skin, lacking the slight texture that made silk stockings comfortable to wear. Most problematically, nylon's superior strength made it difficult to sew. Ordinary cotton thread couldn't match nylon's durability, causing seams to tear while the nylon remained intact. The Union Hosiery Company agreed to produce test batches using experimental techniques that combined nylon legs with silk reinforcement at heel and toe areas and specialized cotton threads for seams. These hybrid stockings solved the immediate technical problems but created new manufacturing complexities. Workers needed specialized training to handle nylon's unique properties. Knitting machines required modification to accommodate synthetic yarn that behaved differently from natural fibers. Quality control testing had to be redesigned for products whose performance characteristics exceeded anything the textile industry had encountered. The most significant breakthrough came through understanding that nylon's molecular structure could be modified after the fiber was produced. Heat-setting techniques allowed manufacturers to stretch newly knitted stockings over precisely shaped forms, then apply controlled heat and humidity to lock the polymer chains in their final configuration. This process created stockings that fit perfectly and maintained their shape even after dozens of washing and wearing cycles. The molecular bonds that were temporarily loosened by heat treatment were formed in the exact positions determined by the shaping forms, creating permanent dimensional stability that natural fibers couldn't achieve. Testing revealed that properly manufactured nylon stockings could withstand stresses that would destroy conventional hosiery. Laboratory samples survived over 300 cycles of stretching and relaxation without showing signs of fatigue. Abrasion testing demonstrated that nylon fibers maintained their strength even after surface damage that would cause silk or cotton to fail completely. Most remarkably, nylon's chemical structure made it nearly immune to the biological degradation that limited the lifespan of natural fiber textiles. By December 1937, DuPont had perfected the chemistry and engineering processes needed to produce synthetic textiles superior to any natural materials. The technical challenges that European experts had declared impossible were solved through systematic American engineering that controlled molecular structure with precision previously reserved for precision machinery manufacturing. Carruthers had proven that American laboratories could not only create synthetic molecules larger than anything nature produced, they could manufacture them consistently in quantities large enough to supply an entire industry. The next challenge would be building production facilities capable of translating laboratory perfection into commercial reality at prices American consumers could afford. The engineering drawings for DuPont's Seaford plant covered 347 blueprint sheets and represented the most ambitious industrial construction project in Delaware history. On December 15, 1938, ground was broken for a manufacturing facility designed to solve problems that had never existed before. The $8 million investment, equivalent to 1/6 of DuPont's entire 1938 earnings, would create the world's first commercial nylon production plant, requiring engineering solutions that pushed American industrial capability to its absolute limits. The fundamental challenge was scaling laboratory precision to industrial quantities, while maintaining the molecular control that made nylon superior to natural fibers. European chemical plants relied on batch processing that produced consistent results through time-tested procedures refined over decades of operation. American nylon production would require continuous processing systems that maintained precise temperatures, pressures, and chemical ratios 24 hours per day, 7 days per week, with tolerances so tight that minor equipment malfunctions could destroy entire production runs worth thousands of dollars. Raw material production presented the first major obstacle. Both hexamethylene-diamine and adipic acid required manufacturing processes that didn't exist anywhere in the world. DuPont constructed specialized facilities at Bell, West Virginia, to produce these chemical intermediates using newly developed catalytic processes that converted readily available raw materials into the precise compounds needed for polyamide 6,6 synthesis. The hexamethylene-diamine plant used high-pressure hydrogenation reactors operating at 400 degrees Celsius and 50 atmospheres pressure, conditions so extreme that the reactor vessels had to be fabricated from specially developed steel alloys. Transporting these raw materials from West Virginia to Delaware required solving logistical problems that conventional chemical shipping couldn't handle. Both compounds had to be maintained at specific temperatures during transport to prevent crystallization or decomposition that would affect polymer quality. DuPont developed heated tank cars with temperature control systems that kept hexamethylene at exactly 65 degrees Celsius and adipic acid at 90 degrees Celsius throughout their journey across the Appalachian Mountains. Insulation systems and heating elements were designed to maintain these temperatures even during winter conditions that could reach minus 20 degrees Fahrenheit. The polymerization process at Seaford demanded precision that exceeded anything attempted in American chemical manufacturing. Stainless steel reactors, each capable of holding 2,000 pounds of raw materials, were equipped with temperature control systems accurate to plus or minus 1 degree Celsius. Automated feeding systems delivered hexamethylene and adipic acid in exact stoichiometric ratios. Any variation greater than 0.5% would produce polymers with inferior molecular weight distribution. The reaction proceeded under carefully controlled nitrogen atmospheres to prevent oxidation that would discolor the final product or weaken polymer chains. Molecular weight control required analytical equipment that could measure polymer chain length in real time during production. Each batch underwent testing using newly developed viscosity measurement techniques that correlated solution viscosity with average molecular weight. Target specifications called for molecular weights between 19,000 and 21,000, with batch-to-batch variation not exceeding plus or minus 5%. Batches that failed to meet these specifications were either reprocessed or discarded entirely, sometimes requiring the destruction of 2,000 pounds of material that had cost over $3,000 to produce. The spinning operation represented the most technically demanding aspect of nylon manufacturing. Polymer chips were fed into electrically heated melting units that maintained temperatures of exactly 285 degrees Celsius. Variations of more than 3 degrees would alter polymer viscosity enough to affect fiber diameter and strength. The molten nylon was pumped through spinnerets, metal plates containing hundreds of holes, precisely 0.004 inches in diameter, machined to tolerances of plus or minus 0.0005 inches. Each hole was individually inspected using microscopes and measuring devices imported from Swiss precision instrument manufacturers. Fiber drawing required mechanical systems that could stretch newly formed filaments at exactly 1,000 meters per minute while maintaining draw ratios of 4 1/2 to 1 with accuracy of plus or minus 0.1. Steam-heated drawing rolls were positioned at precise distances, calculated to achieve optimal molecular alignment without breaking the delicate fibers. Tension control systems monitored the force applied to each individual filament, automatically adjusting drawing speed to compensate for variations in polymer viscosity or ambient temperature. Quality control testing examined every aspect of fiber production using standards more rigorous than those applied to aircraft cables or surgical sutures. Tensile strength testing required specialized equipment that could measure breaking loads accurate to plus or minus 0.5 pounds per square inch. Diameter measurements used optical comparators calibrated to plus or minus 0.0001 inches. Molecular alignment was evaluated using polarized light microscopy that revealed the orientation of polymer chains within individual fibers. The most critical innovation was heat setting, equipment that transformed knitted stockings from simple textile products into precisely engineered consumer goods. Newly knitted stockings were mounted on aluminum forms shaped exactly like women's legs, with dimensions based on anthropometric surveys of over 10,000 American women. Steam chambers applied controlled heat and humidity, exactly 110 degrees Celsius at 90% relative humidity for 12 minutes, while the stockings were held in perfect position. This process caused polymer chains to relax and reform in the exact configuration determined by the aluminum forms, creating stockings that maintained their shape permanently. Production began on December 15, 1939, with a workforce of 230 DuPont scientists and 400 production workers who had undergone months of specialized training. The manufacturing process they operated used precision control systems and quality standards that would not be matched by any other textile manufacturer for the next 20 years. Each day's production required over 50 different quality control measurements, coordinated timing between 12 separate processing stages, and material handling procedures that prevented contamination or damage to polymer chains that had taken weeks to synthesize properly. The numbers that defined successful nylon production reflected American engineering achievement that European textile experts had declared impossible. 15 denier yarn with 60-gauge knit construction. Molecular weight maintained at 20,000 plus or minus 1,000. Draw ratio controlled to 4.5 to 1 with 0.1 variation. Each finished stocking contained exactly 12 miles of perfectly aligned nylon filament, engineered to specifications more precise than those used in manufacturing scientific instruments. DuPont had transformed theoretical chemistry into industrial reality through systematic American engineering that proved precision manufacturing could achieve results that traditional methods could never match. The first shipments of nylon stockings arrived at department stores across America on May 14, 1940, packed in specially designed boxes that protected the delicate synthetic fibers during transport. Store managers had no precedent for what would happen when American women encountered the first commercially available synthetic textile that outperformed natural materials. DuPont's marketing research suggested moderate interest, perhaps 50,000 pairs sold nationwide during the first month. The reality would exceed every prediction by margins that stunned both the company and the retail industry. At exactly 9 o'clock on the morning of May 15th, Gimbel's department store in New York opened its doors to a line of women that stretched for 6 city blocks down 34th Street. Similar scenes played out simultaneously in Chicago, Detroit, San Francisco, and dozens of smaller cities where DuPont had arranged distribution agreements. Women who had heard rumors about stockings that never sagged, never bagged, and lasted for months instead of days had been waiting since dawn to experience American synthetic chemistry firsthand. The initial shipment of 4,000 pairs allocated to Gimbel's sold out completely within 47 minutes. The nationwide sales figures compiled by DuPont's accounting department revealed the magnitude of consumer demand that synthetic textiles had unleashed. 800,000 pairs sold in a single day at $1.35 per pair, equivalent to $29 in modern currency. Total revenue exceeded $1 million, making May 15th the largest single-day sales event in American textile history. By noon, most department stores had exhausted their inventory and were taking orders for future delivery dates that stretched into late summer. Women who purchased those first nylon stockings discovered that DuPont's molecular engineering translated directly into unprecedented durability that revolutionized their daily routines. The polymer chains that had been aligned with mathematical precision during manufacturing distributed stress evenly throughout the fabric, eliminating the weak points where conventional stockings developed runs or tears. A properly cared-for pair of 1940 nylon stockings could survive 6 months of daily wear, a durability improvement of over 1,000% compared to silk or cotton alternatives that typically lasted only days or weeks. The engineering principles that made nylon superior became apparent through everyday use. Silk stockings failed when individual fibers broke under stress, creating cascade failures that rapidly expanded into large tears. Cotton stockings stretched permanently when stressed, losing their shape and developing unsightly bags around ankles and knees. Nylon's synthetic polymer structure responded to stress by distributing load across thousands of individual molecular chains, preventing localized failures that would compromise the entire garment. Even when individual fibers were damaged, the surrounding polymer matrix maintained structural integrity. Consumer testing revealed performance characteristics that exceeded DuPont's own laboratory predictions. Nylon stockings survived washing in hot water that would shrink wool or weaken silk. They dried quickly and retained their shape without the careful handling that natural fiber stockings required. Most significantly, they maintained consistent appearance and fit even after dozens of wear cycles, eliminating the frequent replacement costs that made quality hosiery a significant expense for most American women. The success created immediate supply chain crises that demonstrated both the promise and the limitations of synthetic manufacturing. DuPont's Seaford plant could produce only 12,000 pairs of stockings per day, while consumer demand approached 100,000 pairs daily nationwide. The precision manufacturing processes that ensured nylon's superior quality couldn't be rushed or simplified without compromising the molecular control that made the product revolutionary. European textile manufacturers, who had dismissed synthetic fibers as commercially impractical, suddenly faced competition from American products that consumers preferred over traditional materials. Then global events intervened to transform nylon from consumer luxury to military necessity. The attack on Pearl Harbor on December 7, 1941, immediately shifted American industrial priorities toward war production. Within weeks, the War Department had commandeered 100% of nylon production for military applications, parachutes, aircraft control cables, rope, and tent fabric that exploited nylon's superior strength and durability for life-or-death situations. The synthetic fiber that had been designed to beautify women's legs would instead save American pilots' lives during combat missions over Europe and the Pacific. The military applications revealed nylon's capabilities under extreme conditions that civilian use never tested. Parachutes made from nylon silk performed reliably at altitudes where temperature and humidity variations would have weakened natural silk. Aircraft cables woven from nylon filaments maintained their strength even when exposed to engine heat, fuel vapors, and rapid pressure changes that occurred during high-altitude flight. Military testing confirmed that American synthetic chemistry had created materials superior to anything available through traditional sources. The wartime shortage created a secondary market that demonstrated nylon's perceived value among American consumers. Used nylon stockings sold for prices exceeding their original retail cost. Women carefully maintained and repaired nylon stockings through multiple darning sessions, treating them as valuable possessions worth preserving rather than disposable consumer goods. Black market prices for new nylon stockings reached $10 per pair, nearly 70 times the cost of pre-war cotton alternatives. The tragedy that shadowed nylon's triumph was Wallace Carruthers' absence from the success he had made possible. Depression had claimed him on April 29, 1937, 16 months before DuPont announced nylon to the world. The man who had revolutionized American chemistry and proven that synthetic materials could surpass natural alternatives died believing his work had been a failure. His laboratory notebooks, filled with self-critical comments and expressions of scientific inadequacy, revealed a brilliant mind tormented by perfectionism that prevented him from recognizing his own revolutionary achievements. Carruthers never witnessed the lines of women waiting to purchase products created through his molecular engineering. He never saw American pilots whose lives were saved by parachutes woven from his synthetic polymers. He never experienced the vindication of proving European experts wrong about the commercial viability of large-scale synthetic manufacturing. The greatest triumph in American chemical history was achieved by a man who died convinced he had contributed nothing significant to scientific knowledge. The nylon revolution of 1940 represented more than successful product development. It demonstrated American industry's capacity to challenge established European expertise through systematic engineering and unlimited research investment. DuPont's success proved that precision manufacturing could create synthetic alternatives superior to natural materials, opening possibilities for American innovation that would reshape global industry for decades to come. The molecular precision that created stockings lasting months instead of days had established new standards for what American chemistry could achieve when traditional limitations were abandoned in favor of systematic scientific engineering. The announcement came over radio broadcasts on August 14, 1945, just hours after Emperor Hirohito's surrender speech ended World War II. DuPont would resume civilian nylon stocking production within 60 days, ending 4 years of military commandeering that had made synthetic hosiery unavailable to American women. The company's executives anticipated strong consumer interest based on pre-war sales figures, but nothing in their market research prepared them for the phenomenon that newspapers would later call the nylon riots. Pittsburgh's downtown shopping district on September 21st resembled a battlefield more than a retail environment. Over 40,000 women had formed lines stretching for more than a mile from Kaufmann's department store, all hoping to purchase a portion of the 13,000 pairs of nylon stockings that represented the city's entire initial allocation. Police barriers erected to manage crowd flow collapsed under pressure from women who had waited since dawn for their first opportunity in 4 years to buy stockings that wouldn't develop runs within hours of wearing. Similar scenes erupted simultaneously in Chicago, Detroit, and Los Angeles, where the combination of pent-up demand and limited supply created near riots that required police intervention. The consumer frenzy demonstrated how wartime scarcity had elevated nylon stockings from luxury items to symbols of American prosperity and normalcy. Women who had spent 4 years darning silk stockings, drawing seam lines on their bare legs with eyebrow pencils, or wearing cotton hosiery that sagged and bagged within hours, now viewed nylon as liberation from the compromises that wartime rationing had imposed on their daily lives. The molecular engineering that Carruthers had perfected in the 1930s represented not just superior textile technology, but proof that American industrial capability could restore pre-war quality of life. DuPont's post-war production maintained the precision manufacturing standards that had made 1940 nylon stockings revolutionary. The Seaford plant continued operating with molecular weight control within 5% variance, draw ratios maintained at exactly 4.5 to 1, and heat-setting processes that aligned polymer chains with mathematical precision. Quality control testing remained more rigorous than standards applied to aircraft components. Each batch underwent tensile strength verification, molecular alignment analysis, and dimensional accuracy measurement using equipment that most universities couldn't afford. The engineering specifications that defined authentic nylon quality became apparent through extended consumer testing that revealed dramatic differences in durability and performance. Properly manufactured post-war stockings using DuPont's original standards could survive 3 to 6 months of regular wear without developing runs, tears, or permanent stretching. The polymer chains that were aligned during controlled drawing processes distributed stress evenly throughout the fabric, preventing the localized failures that caused immediate runs in inferior products. Women discovered they could wash nylon stockings in hot water, dry them quickly, and expect consistent fit and appearance even after dozens of wear cycles. The precision that created superior performance required manufacturing disciplines that increased production costs significantly compared to conventional textile processing. Temperature control during polymerization consumed substantial energy to maintain 285 degrees Celsius processing temperatures within 3-degree tolerances. Molecular weight testing required expensive analytical equipment and trained technicians who could interpret viscosity measurements accurately. Heat-setting operations demanded specialized aluminum forms, machined to precise dimensional tolerances in steam chambers that maintained exact humidity and temperature combinations. But American consumer culture was evolving toward convenience and disposability rather than durability and precision craftsmanship. The suburban lifestyle that emerged during the 1950s emphasized time-saving and labor reduction over product longevity. Fashion trends accelerated, encouraging consumers to replace clothing items for style reasons rather than wear-out failures. Most significantly, the birth rate increases that created the baby boom generation placed new demands on household budgets that made expensive, long-lasting products less attractive than cheaper alternatives that could be replaced frequently. The transformation began with Allen Gant Sr.'s invention of pantyhose in 1959 at his Glen Raven Mills facility in North Carolina. Gant's innovation combined stockings with panties into a single garment that eliminated the garter belts, girdles, and complex fastening systems that had made traditional hosiery uncomfortable and time-consuming to wear. The convenience appeal was immediate and overwhelming. Women could put on pantyhose in seconds rather than minutes, and the integrated design eliminated the constant adjustments that separate stockings required. Manufacturing pantyhose economically required abandoning the precision standards that had made DuPont's original nylon stockings superior products. Automated circular knitting machines could produce pantyhose legs in 90 seconds each, but this speed came through relaxed tolerances that would have been unacceptable in 1940. Molecular weight control dropped from plus or minus 5% to plus or minus 15% variance. Draw ratios loosened from 4.5 to 1 precision to approximately 3 to 1 with much greater variation. Heat setting became optional rather than mandatory, eliminating the dimensional stability that had made original nylon stockings maintain their fit permanently. The cost pressures that drove these manufacturing compromises reflected broader changes in American industrial philosophy that prioritized automated production efficiency over precision craftsmanship. Labor costs had increased substantially during the post-war economic boom, making the specialized workers who operated DuPont's precision equipment expensive compared to automated systems that required minimal human supervision. Raw material costs had also risen, encouraging manufacturers to use lower-grade polymers that met minimum performance requirements rather than the superior materials specified in original nylon formulations. The numerical comparison between original 1940 nylon stockings and modern pantyhose revealed the extent to which manufacturing standards had deteriorated in pursuit of lower costs and higher production speeds. Original specifications called for molecular weights between 19,000 and 21,000 with 5% maximum variance. Modern pantyhose typically used polymers ranging from 12,000 to 18,000 molecular weight with 15% variance acceptable. Draw ratios had decreased from 4.5 to 1 precision to approximately 3 to 1 average. Heat setting that permanently aligned polymer chains was abandoned entirely in most production facilities. The durability differences were immediately apparent to consumers who had experienced both products. 1940s nylon stockings lasted months with proper care and could survive multiple darning repairs when minor damage occurred. Modern pantyhose developed runs within hours or days of first use, with some products failing before leaving the store. The polymer chains that lacked proper alignment created stress concentration points, where tiny snags propagated into large tears that rendered the entire garment unusable. Museum collections and vintage clothing archives provide physical evidence of the superior engineering that characterized original nylon production. 80-year-old stockings stored in proper conditions remain intact and functional, demonstrating the long-term stability of properly manufactured synthetic polymers. The molecular precision that Carruthers and his team achieved through systematic American engineering created products that modern cost-cutting manufacturing methods have never matched. Sometimes the old way was indeed better. DuPont's 1940s molecular engineering created stockings that lasted years, while modern automation produces pantyhose that barely survive hours of use. The difference represents more than just declining quality standards. It demonstrates what American manufacturing loses when precision craftsmanship is abandoned in favor of automated efficiency and profit margin optimization.